the order of a rate of reaction is expressed as the power that you need to raise concentration to. And we're going to just have a quick explore of what that means. So let's imagine I have a graph here. I have y equals x plotted on here in red. We just have x across the bottom and y up the side, as you would expect. I have y equals 3x in blue, and I have y equals pi x over 2 in purple. What do they have in common? They are all straight lines. Why are they all straight lines? Well, because for all of these, y is proportional to x. Okay, we are multiplying x by a different function, but x itself is raised to the power of 1 in each case. Okay, so in each of these graphs, because y equals x or y equals 3x or whatever it is, in each case x is always raised to the power of 1 and nothing else. So what's this got to do with rates? Well, if you were to take a graph similar to this, and you would say, okay, well, I'm going to change y, so y equals rate, and I'm going to plot my reaction rate up the side. And I'm going to change my x, so that the x-axis now represents the concentration of something. Then we can find out what effect the concentration has on the reaction rate using a graph. So here we go. I've put concentration of chemical A in, so that's square brackets around the A. That just means concentration of A, and that's in moles per decimeter cubed. Up the side, I've got rate, which is measured in moles per decimeter cubed per second, and I've got a straight line there. So rate is proportional to whatever is on the x-axis raised to the power of 1, which means that as what's on the x-axis is the concentration of A, rate is proportional to the concentration of A raised to the power of 1. Okay, so where do we go from here? Well, we can actually work out, as with any straight line, y equals mx plus c, but you'll notice that this goes through the origin because at a concentration of 0, there is no rate of reaction. Okay, so we have through the origin, so there is no need to worry about the plus c, we just have y equals mx, and we can write that as rate equals the gradient multiplied by the concentration, and that gradient we call the rate constant. So we say that this is an order of 1 because we have our concentration raised to the power of 1, and we say that the gradient of this line is the rate constant K. So if A was the only chemical in this reaction and we saw this pattern, we would write this at the bottom is a rate law, which is y equals mx basically, but we are calling it rate equals the rate constant multiplied by the concentration. And I've left the to the power of 1 in there because, and you don't have to do that. Just as a reminder that this is how we know it's an order of 1. So what are the other possible orders? Well, if we take another collection of lines here, you'll see that this is y equals x squared in red, y equals 2x squared in blue, and y equals x squared over 4 in purple. And you can see that they've all got the same sort of shape to them because they're all based on a curve of x squared. But again, the change in gradient here is different because of the functions that we've applied to x squared. But for all of them, y is proportional to x squared. And again, if we take the same idea and we put concentration across the bottom and across the x-axis, and we put rate up the side, we get a slightly different type of order, because now the rate is proportional to x squared, and so if x is concentration of A, we get rate is proportional to A concentration squared. Okay, and what that means is that when we put this into words and we say it's got an order of, we now have a different number that the concentration is raised to the power of. We say it's an order of 2. So we have a rate order of 2. Again, if A was the only chemical in this reaction, we could write a rule for this graph where rate equals K multiplied by A squared. Now it's slightly harder to work out K here. There are various different ways that you could do that, but that is where the rate law for this graph would come from. Okay, K multiplied by A squared for this shape of graph. The other possible order is this. You'll notice in each of these ones I've done y equals 4x to the power of 0, y equals pi x to the power of 0, and y equals x to the power of 0 multiplied by 6 over 9. Okay, and in each of these cases, whatever function I've done to x to the power of 0, all of these lines are horizontal. Okay, y is proportional to x to the power of 0. So what's going on here? Well, anything raised to the power of 0 is, of course, 1. Okay, so for the first one, y equals 4x to the power of 0 is basically saying y equals 4 times 1. Y equals 4. So it's a straight line across the graph. And we call this a 0 order. What we're saying is that whatever we do to x, we're going to have the same value of y. Okay, and again, if we put that onto our concentration equals x and rate equals y, if we change the concentration of a reactant and we get no change in the rate whatsoever, then what we can say is that rate is proportional to the x to the power of 0, or proportional to 1 basically, and therefore rate is proportional to the concentration raised to the power of 0, which is still 1, and therefore the rate order we say is 0, and we would write that as rate equals K multiplied by A to the power of 0. So in this case, we can say rate is basically equal to the rate constant. So 3 shapes of graph to remember when you're looking at results from a reaction where you're plotting concentration of a chemical up against the rate. If changing the concentration has no effect on the rate, it is 0 order. If the change in concentration is proportional to the change in rate, it is first order. And if you have a rate where the relationship is the concentration to the power of 2 is proportional to the rate, you have second order.